Hello everyone, in this video I'm going to be talking about how to make ethers from alcohols, alkyl halides, and alkenes, and I'm also going to talk about Williamson synthesis reaction to form the ethers, and that's typically done from alcohols and alkyl halides with the primary alcohol, and that actually makes symmetrical ethers, and it's going to proceed with the mechanism of an SN2. So typically I have this primary alcohol, and in the presence of an acid, it's gonna go ahead and make a symmetrical ether where I will have the same chains on both sides of the oxygen. And those same chains are actually coming from the same reactant. It's just being reacted twice or with itself. So how does the mechanism really work? So the first step is just going to be the protonation. So obviously I got this sulfuric acid used as an acid catalyst here. So let me go ahead and write down this H2SO4 in the form of structure. So this is how it looks like. And I can obviously use one of the protons on the sulfuric acid to protonate that oxygen there. And in the process, I'm just going to go ahead and copy this down here and change the color there. So I already had a hydrogen, obviously I get another hydrogen there. That leaves you with only one lone pair of electrons on the oxygen, so this gets a positive charge. Now, this is a relatively good leaving group because it's got the water now. And then in the next step, what happened, I get the same compound, the same alcohol is going to do the nucleophilic attack on this one. Now, remember, this is, if I get rid of the water here, it's going to make it a primary carbocation, which is not going to be stable. So as a result, it actually do an SN2 type reaction where this attacks right here and the water leaves at the same time. So that's why it follows an SN2 mechanism. So remember, I have those two right there, and I can go ahead and change the color here real quick. I'm just going to go ahead and change this to a different color so that you guys can see the different color combination there. So obviously I got this two methyl groups. I'm going to make a new bond here. So that's your new bond right there. And then you're going to have the oxygen coming from that. And then you have this other ethyl group attached there. Remember this, the hydrogen is still there. And then eventually you're going to make the product. And the way you make the product, so remember you use the sulfuric acid as your catalyst in the beginning, so you want to go ahead and bring the conjugate base back to grab this proton, and that's going to restore the electron density back onto this oxygen, and it's going to make the end product, and you're going to retrieve your sulfuric acid so that it can be reused again. So typically this particular reaction works with primary alcohols. Secondary alcohols and tertiary alcohols would be hard because they will do elimination instead. This could also do an elimination if you heat it up to a higher temperature. So typically when you're trying to make an ether, symmetrical ether from alcohols, we would have to heat it up to somewhere around 130 degrees Celsius. But if you heat it up higher, then you may get an elimination reaction. So it may not be the best way to make the ethers because you're always going to have an acid reaction or elimination reaction as in a competition going on. So there are some other ways you can make it. In addition, this also makes only symmetrical ethers. You can't really make an asymmetric ether. So let's talk about how you can actually make an asymmetric ether, and that's also called an Williamson synthesis reaction. So in the first reaction, I can go ahead and have any type of alcohol. So it doesn't really have any restrictions on the type of alcohols you can have in a primary, you can have in a secondary, and even you can have in a tertiary alcohol. All right, and as far as their alkyl halides go, it prefers to have a primary alkyl halide because if you use in a secondary and tertiary alkyl halide, you're going to get an elimination reaction over the substitution reaction. So alcohols you can have whatever you want, but for the from the Alkyl halides, you want tends to have either a primary alkyl halide or maybe benzoic halide. That's going to be the same thing. So the first reaction is going to be done in the presence of a strong base, and typically used NaH, or either you can use some metal, you can even use sodium. So let's suppose in NaH case, I got this H minus, and it's going to go ahead and grab this proton here. So I'm going to go ahead and change that with the bond here. All right, so it's going to go ahead and grab this proton here, does an acid-base reaction, and you create this alkoxide here. So you got this alkoxide made here. All right, and then the side product here is going to be the H2 gas, which is just going to leave the solution. So that's why it works really well. This is a highly exothermic reaction. So if you do this in the lab setting, you got to be really careful because it's a super exothermic reaction. And then in the next step, I can go ahead and use any alkyl halide. So let's say I'm going to go ahead and use an ethyl bromide here, and this ethyl bromide, it's going to run in an SN2 type of reaction, because remember, this alkoxide that you just created, it's a strong nucleophile and it's a strong base, but since you're dealing with a primary alkyl halide, it's only going to do an SN2 reaction. So if you do in a secondary or a tertiary alkyl halide, it's going to do an elimination instead, especially with a tertiary, and then with a secondary, you'll get a mixture of a substitution and an elimination. So I can go ahead and do this here. Oops. And this leaves. And then I'm just going to copy this down here. You make this product here. Keep track of your carbons. So this is a way of making an asymmetric ether in this particular case. So let's look at an example. Let's suppose I'm trying to make this particular ether here. And what are two possible ways you think of? And then one possible way is not going to be, one of the ways is not going to be good enough way making this particular ether. So think of this way. But suppose if I go ahead and start out with this, and then I'll say, okay, in the first step, I'm going to use NaH, and then in the second step, I'm going to use this tertiary alkyl halide here. And then the question would have been, are you going to get this particular product? And the answer is going to be no, I'm not going to get that, because once you create this ethoxide here, it's going to run an elimination reaction. So your product instead is going to look like this. So we'll have this, and plus you're going to have technically the ethanol back. So that's not the best way of making that particular ether. So instead, what you want to do is you can do the other way around, where I want to go ahead and use this tertiary alcohol, because remember, the alcohols don't really have any restriction in terms of what it could be. And then I can go ahead and use some sort of base, strong base. I can use KH here. So, instead of Na, you can use potassium as well. And then second is I can go ahead and use this alkyl bromide here, or ethyl bromide here. So then in that case, you will get this particular product, because the alkoxide you create, which is a strong nucleophile and a strong base, but then you're using in a primary alkyl halide, which is only going to do an SN2 reaction, but this tertiary alkyl halide will do an E2 here instead of an SN2 reaction, so you get an elimination product. So this is something you got to be really careful with, what type of alcohol and what type of alkyl halide you want to use when you're trying to create the Williamson synthesis ether reaction. Okay, you can also, if you want to create ether from the secondary and tertiary alcohols, you can do so, but you just have to be, you can't just really use a base. You're just going to have to do an SN1 type of reaction. So suppose I'm doing this one, and that's going to hold true for the tertiary alkyl halide as well. So if you recall, your SN1 mechanism is you're going to have a loss of leaving group. So first leaving group leaves, and then you make this carbocation. And once the carbocation is made, you want to make sure you can check if you can make it a more stable carbocation, but this is in a secondary carbocation, and you can't really make anything more stable than that. And then in the next step, I can have this methanol here. So obviously you can have ethanol as well, or some other ether, some other alcohols as well. So this could technically do a top attack, and this could do a bottom attack. So that's another thing you want to be careful with. So if it does a top attack, something like this, then my product or my intermediate, next intermediate technically is going to look like this. Got an hydrogen there, plus there, and then I'm going to have mechanistically the bromide coming in and grabbing this proton. And this goes back and restore the electron density on the oxygen. So you end up making this ether that's actually asymmetric. So it does go ahead and do with an SN1 type mechanism. However, so the downside of that would be, like I said, you can have a top attack or a bottom attack. So you have a possibility of making a pair of enantiomers there. So where this could be going back into the page and this could be coming out of the page. So you have to only worry about this if there is a chiral center. If you don't have a chiral center, you don't really have to worry about it. So the tertiary alkyl halide would work very similar to just like we had here. So then, in addition to that, you can also get ethers from alkenes, and you have learned about creating alcohols from alkenes by adding water and acid. But if you replace the water with some sort of alcohol, then you can actually create an ether. So I'm still going to be using an acid as a catalyst here. And typical acid here that's going to be used would be H2SO4 in the presence, and then I can go ahead and use something like CH3OH. So I'm not really using water here because water would make the alcohol. So it's a very similar reaction that we have learned how to create alcohols from the alkenes. So here, what this end product is going to look like, it does in a Markovnikov's edition. So I can have this OCH3 either coming out of the page, and that will push this methyl go back into the page, and then obviously I can have the enantiomer of that as well. So since it creates a carbocation and there is a possibility of carbocation rearrangement, it will make an racemic mixtures at the end of the day. So that's the only downside that you're going to get to a mixture of products. So how does this really work mechanistically? So real quick, obviously I'm getting the acid here from the sulfuric acid. So I can go ahead and protonate this using the double bond. Double bond is acting as a nucleophile here. And then one of the carbons is going to get the hydrogen, and the other carbon is going to becomes electron deficient. So I'm going to go ahead and add, so I'm going to call this one here for two here just for my own sake. So I want to be able to create a carbocation at the first position because it's going to be a tertiary carbocation. So you want to go ahead and add the hydrogen on the second position. So then you get this particular carbocation here. And then after that, it's kind of similar to what we did earlier with this alkyl halide, secondary and tertiary alkyl halide. So I can go ahead and have this CH3OH coming in and doing either the top attack or the bottom attack. All right, so when it does the top attack, it's going to be obviously coming out of the page, and if it does the bottom attack, it's going to be going back into the page. So I'm not going to show both of them, but I'm just going to show only one of them here, just for the sake of time here. And typically, even when you draw the mechanisms in the exams and in the homeworks, you don't really have to show both of them. You want to be able to draw both of the products at the end of the day, but you don't have to show the mechanisms for both of those guys. So this is what it's going to look like, and then eventually you're going to make the product, and your product, obviously, this is protonated right now, so I want to go ahead and have this oops, HSO4, 1 minus coming in and grabbing this proton here. And it's going to restore the electron density back onto the oxygen. So the downside of this particular type of reaction is that you make a carbocation and there's going to be a possibility of carbocation rearrangement. So for example, if I do this next example here, and I'm going to be doing the same type of reaction. So I'll say I got H2SO4 and I'm going to be using CH3OH. So when I run this reaction, the product actually going to look like this. I'm just going to go and copy this down here, erase part of it, and its product is going to look like this. You're going to have an oxygen here and metal there. So you expect that this ether would be make at the second position, but it's not at the second carbon, but it's not. That's because there's going to be carbocation rearrangements. So how does that really work? Uh, it's a slight mechanism. I'm not really going to show too much here, but you make carbocation first. So if you're using this HSO4 rare, so you protonate that. So once you protonate this, once you do this nucleophilic attack from the double bond, you're going to be making this particular carbocation. Now, this is in a secondary carbocation, and then from the secondary carbocation, I can have this 1,2 hydride shift, because if I can move this positive charge to the left side, then I would be able to create a more stable carbocation. So it's going to have a 1,2 hydride shift, okay? And then I'm going to end up getting this tertiary carbocation. And then from here, you can do the attack. So I'm not really going to show that part. And remember, this is not a chiral center anymore because you got two methyl groups on it. So you don't really have to worry about the chirality or the stereochemistry there. Now, what's going to be a better way of making the ether where you don't have to worry about doing the carbocation rearrangement? So there is a way, like suppose I'm using the same reactant that just did up there, and I'm trying to make actually this product here. All right, so I put the stereochemistry in there as well. So here, we're still doing Markovnikov's addition, but we're trying to make sure there is no carbocation rearrangement. So this could technically happen if you do an alkoxymercuration and demercuration. So this is kind of similar to the oxymercuration, demercuration. In oxymercuration, demercuration, you use water, but here you're actually going to be using an alcohol. So in the first step, we do this obviously with mercury acetate. And then instead of using water, I'm going to use CH3OH here because that's what I'm adding here to create the ether. And obviously you can have any other alcohol here depending on what type of ether you're trying to create. And then the second step is going to be use of this reducing agent as a source of hydride. So this actually prevents any carbocation rearrangements, but this also goes with the formation of a racemic mixture if there is a chiral center. So that's the only downside of it. But if you're not worrying about the stereochemistry, then you will be able to get a a perfect Regis selectivity here where you only make Markovnikov's addition there. So how does this really work? Typically, you don't have to know the mechanism for this, but I'll show you why it doesn't really do any carbocation rearrangements. So I got this mercury acetate here. So that's how it looks like. And I got a lone pair on the mercury. So I'm going to have this pi bond attacking, and then this mercury going back and attacking the other carbon. So it kind of makes, and then you lose one of the acetates. So the intermediate kind of looks like a mercurium ion, where this mercury is actually attached to both of those carbons here, just like this. You still got one acetate group intact in there, and they got a positive charge on this one. And then in the next step, you get this CH3OH, which is not a great nucleophile, so it's going to look for where to attach. So between this, let's call this one and second position. The second position, kind of being in a secondary there, it's going to have a better positive character there. So it's going to attack right at the second position. So it's still due in a Markovnikov's addition, and then this breaks open right there. And then let's going to copy this down here. Okay, let me erase some part of that. So I still got this HG OAC, and then I still got this. I'm going to draw that coming out of the page. So remember, this could do the attack coming out of the page, or this could do attack and going back into the page. So that's why you get to racemic mixture. So, but I'm only going to show one of them there just for the sake of time. So in the next step, I can use the acetate to grab that proton. So remember the CH3COO, which is just the OAC minus. So this is going to go ahead and grab that proton, and it's going to restore the electron density back onto that oxygen. So remember there's a bunch of electrons on that oxygen. So it makes an acetic acid. Okay, so this is what you make, and then finally, just going to go ahead and draw that down here. We use NaBH4. So NaBH4 is a reducing agent, which is kind of a source of hydride. So H minus coming from this reducing agent is going to do an attack right here. And it's going to get rid of that mercury that's there. So this is how you're going to be making an ether here using alkoxy mercuration, demercuration, and obviously you're going to have an enantiomer of that as well. So those are some of the common ways of making ethers. Obviously, Williamson synthesis reaction is pretty common out there, but the other ones you could be used as well in the synthesis. If you have any questions on any of those, feel free to leave any comments in the section below.